A little story to wake you up. So does everybody know what a genie is? So a genie arises in many stories. It goes like a person finds an old lamp or so, which is very dirty, and then they rub the lamp, and there comes out a lot of smoke, and then a ghost comes out, which they call the genie. And then the genie gives you 3 wishes, or 2 wishes, or 1 wish. So you can wish whatever you want, and then you get a car, or you get all the power you want, or something like this. And so sometimes I wish I have a genie who gives me wisdom. And another thing I wanted to tell you about is about these very difficult problems you find in the Clay Institute, for example. They have these $1 million mathematical open problems. And I recommend for each of you to work on these problems at some point. So I do that too. Whenever I'm maybe bored with my stuff or something, I just take the Navier-Stokes equation problem. So you know there's the problem to find strong solutions in 3 dimensions for the Navier-Stokes equation. It's still unsolved. And sometimes, when I have nothing else to do, I look at it and maybe try a little bit and so on. I never solved it, of course, otherwise I would be very famous. And then one of these days I did the Navier-Stokes problem, worked around and didn't get any solution. And so I thought, well, I go and get a coffee. So then I went over my campus in Alberta and then I saw something shiny in the bushes. And so then I looked and what is this? And it was an old lamp. So I picked up the old lamp and it was very dirty, so I rubbed it to clean it up. And then boof, so out came a genie. And he said, I'm the genie of wisdom. You have 1 wish which I will fulfill. And so I thought, oh, what a good coincidence. So this guy can certainly help me with the Navier-Stokes problem. So I told him, I was working on the 3D Navier-Stokes problem, and can you help me? And then he said, this is a very, very hard problem, and has not been solved for many years. Don't you have anything else you can ask me? So I said, well, at that time I also had a little problem with my wife. I said to him, I really would like to understand the women. And the genie looked at me and then he took out a piece of paper and a pencil and he said, let's look at the Navier-Stokes equation. Hope so. So, he's still working at it, so it's still unsolved. So let us look at the transport equations then. So we are basically done with the one-dimensional case. I've shown you the basic theory, how the equations work. And I've mentioned a lot of applications, but I didn't show you any details of the applications. There was just not enough time. But now let's move it up to higher dimensions. So now we are really interested in these kind of orbits where particles move in 2 or 3 dimensions, depending on the situation. And you have information on the path. Now in 1D, we had only 2 directions. We could go right or left. Now let's say in 2D on the blackboard, we have all angles, all possible angles, right? So we have a continuum of directions. Not only 2, but a continuum. And so it makes it very quickly much more complicated. And so now we are interested in a population density which depends on time and space, but also on the direction, or also on the velocity, which I call v. Okay, so then x is in Rn, time is non-negative, and v is in a set capital V in Rn, which is compact. And this is a very important property here. So later I will write down an equation which looks a little bit like the Boltzmann equation, which is known from physics. But in the case of the Boltzmann equation, this set of velocities is not compact. But here it is compact, and we gain quite some nice properties from this compactness. So what is v? So for example, v could be a set of speeds s1, s2, and then any direction. So with Sn minus 1, I mean the unit disk in n dimensions, or the outside of the unit ball. So this is any directions, but then the length of this vector could be in an interval s1, s2. So you can choose s1 to be 0, and S2 to be the speed of light, then you have a nice compact set, and every speed is in that set, that's for sure. Or often I use S times Sn minus 1. This means you have any direction, but you have a fixed speed S. And actually, in most of my examples, I will use this case. Whatever I do can be done either way, but in this case, it is just easier to write down the integrals because you just do not have to integrate over this bit. So this just makes the formulation a little bit easier, but everything can be done for both cases here. Okay, so let's write down the transport equation. So we have pt plus v times gradient p. Like before, if I write 0, then this is transport in direction v with velocity v. But now the particles change direction. And if you remember the second formulation I had just earlier, I use that here too. So they change direction with the rate mu. And here I write down the arguments. So a particle which has velocity v, it switches and chooses a different velocity. And then I have to balance what is the new velocity it chooses. There's an integral kernel v prime, p of tx v prime, dv prime, and we integrate over v. Now these are all particles which have velocity v prime first, but then they switch from v prime to v. So these are all other particles which switch into my direction v, and they will be added to that equation for v. Okay, so this is called a transport equation. The Boltzmann equation, as I say, is very similar. Transport equation. Okay, and so what is which? So mu is the turning rate. So which means 1 over mu is the mean run length, or mean run time, actually. Mean run time. So the time between different directions is 1 over mu. That's another way how this can be measured. And then t of v prime is the turning angle distribution. Or we call it the turning kernel. And we turn from v prime to v. From v prime to v. So it's kind of written backwards. So you turn from v prime into direction v. This is a standard notation which has established itself like this. So I keep it like this. It means you change from v prime to v. So let's add some names. So maybe the first name I should mention is Struck in 1974. Papa Nicolau. In 1975. So you looked at this model from a stochastic point of view, but not yet from a biological point of view. This was still the physical context. But then into the biological context, it came by Othmer, Dunbar, and Alt. Othmer, Dunbar, Alt, 1988. It's already an old paper, but it is a wonderful paper. So if you're ever really interested to work on this, it is a very good place to start. Othmer, Dunbar, Alt. Then myself and Othmer, we have done 2 papers in 2000 and 2001. And then there's a textbook by Benoit Pertam. Textbook specifically about kinetic equations in biology. So it's a very good book you can look at too. So 3.1, let's look at the mathematical setup. So basically what I would like to do is to do the same thing, to find like a Cattaneo equation and then find a telegraph equation and then find the limit. But of course this is not so easy in this case, right? Actually what you can do, you could maybe integrate this by v. So for the Cattaneo model I added the 2 equations, u plus plus u minus, And adding is integration, so I could integrate this over all velocities v. Okay? And this can be done, and then you get a conservation law. But from here, you get the flux term, v times p. And so then you can multiply the whole thing by v, integrate, and you get something for the flux. But then a second moment arises. So then you multiply the thing by v again, and you get higher and higher and higher moments, and it never stops. So in the one-dimensional case, it stops after 2 equations. In this case, it never stops. So we have to do something else. Okay, so I work in L2 on this compact set V, and K is a cone in L2, cone of non-negative functions. And then I define 2 integral operators on L2. So the first one is called T, L2V in L2V, which is just the integral which appears in our equations here. So T of phi is integral V T VV prime phi of v prime dv prime. Okay, so I took out the right-hand side here of my equations, but I only worry about the v dependence. So time and space, this comes later. So for this operator, this acts on the v dependence. You put in a function on v, and you get out a new function on v, right? So here's still a variable v sitting, so you get a new function of v. Okay, and then we need the adjoint also. The adjoint operator, so this is T star, and T star is just by flipping the prime of the integration. So T star phi is integral T of v prime v phi of v prime dv prime. So just in this kernel function T, v prime and v, the order has switched. And this gives you the adjoint operator. And I need both of them. Okay. So now I have a set of basic assumptions. And I'm always drawn between first motivating the assumptions and then writing them down, or first writing them down and then motivating it. I think it's better to write them down first, then we have them all in one place, and then I talk about each of them one by one and tell you what it really means. If I write them down now, it is in some place not so clear what it means or why I do it. So let me write them down, then explain them. And this will basically take all of today's lecture to explain these. So the first one, T1, is T of VV prime larger or equal 0. Integral V T VV prime dV is equal to 1. Well, these are not complicated conditions, so the kernel is non-negative, and it should integrate to 1 over the first variable. And then the double integral VV of T square VV prime dv prime dv is bounded, so it's some kind of a regularity condition. So this is not a hard condition. But T2 is more interesting. So there is a function u0 in this cone, which is not the zero function, and a constant rho positive, and there exists a natural number n such that for all v and v prime in v star v, we have one of two conditions. We have either A or B. A will relate to the adjoint and B will relate to the operator itself. It turns out I need the condition only for one of those two, and everything works. So that's why I have case A and B now. So either I have a u0v is less or equal t to the n v prime v less or equal rho u0 of v, or b u0 of v, so the same thing for v prime rho u0 of v. Yep. So it's clearly it is a boundedness condition, right? It's clearly a boundedness. So this function u0, whatever it is, it bounds t to the n or t adjoint to the n. But of course, I need to tell you what t to the n is. So where t to the n is the nth iterate of t, and so this is defined to be t to the n of v prime is the integral of v, many integrals of v, t v prime w1, t w1 w2, t wn minus 1 and v, and then ddw1, dw2, dwn minus 1. I know it's a monster, but so you take n copies of t and you're integrating them with the w's, and then you get a new kernel, and you call this new kernel t to the n. Yeah, it looks like a monster, but you will see later it's actually quite cool, because we can really use it for the biological applications later. Okay, so then T3, we take this operator T, okay, and we make the norm, but only on the orthogonal complement of the functions which are constant. So 1 is the function constant 1, which is a member of L2 space, and then I take the orthogonal complement in L2 of this function, and so this is a norm, and then this norm has to be less than 1, where L2v is split into the constant functions and the orthogonal complement of the constant functions. And so I need this estimate only on the complement. Okay. So again, it is, for now, if you see it the first time, it's really hard to make out what it really means for the biology or so, but we come to this. And then T4, I want it on the same thing. So T4 goes here. T4 is the integral v t of v prime dv prime is also equal to 1. So T4 is very similar to T1. Here in T1 I integrate over the first variable, and in this one I integrate over the second variable. And it turns out that one is very natural and the other one is very restrictive. And I tell you which is which. So let's look at these. Let's call it maybe consequences. So where I would like to go is something like a Kindman theorem, which we have also seen in Dr. Matano's talk. I want to find a leading eigenvalue, a leading eigenfunction of these operators t and t star. That's what I need. And there's quite some build up before I really get there. So let's look at T1. So what follows from T1? So first of all, T dot v prime. So for each v prime, T of v is a probability density or probability measure, because it integrates to 1 and is non-negative. So it is a non-negative probability density on V, and then also it also means in biological terms, if a particle comes with velocity v prime and relocates to any other velocity v, then it will find another velocity v. So the integral over the target size v is equal to 1, which means the particle doesn't get lost. If it changes direction, it doesn't get lost. So that's kind of particle conservation. So also particle conservation. So, and this is the condition which I think is quite natural. We don't want to lose anything by reorientation. And then this condition that the integral over t square is bounded basically means t is in L2, v cross v. So it's just an L2 function of two variables which are the velocities. And this makes the corresponding operators. Oh, sorry, now I mixed up the t. So this makes these operators to be Hilbert-Schmidt operators. There's a special name for these. So t and t star are Hilbert-Schmidt operators. So I'm not going to write down the definition of Hilbert-Schmidt operators because it is a definition. So if the kernel is in L2, then by definition these are called Hilbert-Schmidt operators. Okay, but for these operators we have some very nice property. That's a theorem which is in the book by Holmes and Sundar. And which says Hilbert-Schmidt operators are bounded and compact. Bounded and compact. Yeah. So this is cool. So now these integral operators, which I defined here, t star, they are compact operators. And I told you already that I'm interested in the spectrum. So what do I know about the spectrum for compact operators? So somebody who can tell me what do we know about spectrum of compact operators? Point spectrum, very good. What else? So can there be accumulation points in the point spectrum? Yeah, I think I heard the right answer. So there can only be one accumulation point at 0. So they could converge to 0, but they don't have to. But that's it. Otherwise, we have point spectrum. Yeah, very good. And so that's a nice property, which follows from very simple assumptions here. Okay. So then also these operators t and t star are non-negative. They're non-negative, which is just the first condition because the kernel is non-negative. So that's pretty clear. So next condition T2. So T2 is much more interesting with this function U0. And this is an idea from Krasnozelsky from the 60s, 1964. And so if Dr. Matanu were here, he would be very happy because now I present a result of a Russian scientist which is not forgotten, but which we are using. So it's a theory of Krasnozelsky. So yeah, maybe I can write this here. So if I look at T2a, then this implies, which I will show in a second, but I write it already. This says T star is U0 positive in the sense of Krasnozelsky. And then T2b says the same thing for T. So T is U0 positive. Of course, now I need to explain what I mean by this. Okay, so let me do that here. Definition. Krasnozelsky, 1964. There's actually another interesting story with Krasnozelsky. So I knew I need the result from Krasnozelsky to move on and all this. And so I looked up his paper, and then of course it is in Russian. And my Russian is not very good. My Russian is as good as my Korean. So that doesn't really help. And then I forgot about it and did something else. But at some point I came back to it. I really wanted to do it. Where was I? Yeah, Salt Lake City. Or at the time I was in Salt Lake City. I went to the math library. I looked up Krasnozelsky's paper again. And all of a sudden it was in English. And I like, what? What happened? So what happened is this has been translated. And there's like a journal which is Translations in Mathematics or something. And it just in the 70s or somebody translated it. And so then it was in English. It was very good. Okay. So this is available in English. So let's say X is a Banach space. K in X is a cone. L is a linear map in X. Linear. So all the situation we have here, then we say L is positive if it maps a cone into itself. Yeah, now there's this issue as well with positive and non-negative. So some people call this non-negative if the cone maps into itself. And if positive solutions stay really positive, they call it positive. Now Krasnozelsky calls this weaker property positive, and then he has a higher level which he calls U0 positivity, which I define next. So this is positive. Right. So B, let L be positive. L is U0 bounded from below. If there is a fixed U0, which is not the zero function, such that for all phi in the cone which are non-zero, there exists an n and an alpha, so that alpha U0 is less or equal L to the n phi. So again, there's this magic n arising, so we are not only concerned with the function, we can look at a higher iterate of the operator, so L to the n is n times application of L. And then if I apply to any function in the cone, I stay above a given function U0. So U0 is kind of our measure of positivity for this operator. All right. So then C, we can do U0 bounded from above. Same story. So then we have L to the n tilde phi is maybe less or equal beta U0. So then this n can change and the beta can change, but we have an upper estimate. And then D, U0 positive, is both. What is it? B plus C. So we want to have U0 bounded from above and U0 bounded from below. And if you look at my definitions, T2, right, so this looks already like these conditions here. So I have a U0 and the T to the n is between U0 and rho times U0. And then I need another property. K is reproducing if for all phi in X, there exists phi plus and phi minus in the cone, and phi is the sum of those two. Minus phi minus. So I can split up any given function, I can split up in a positive and negative part. That's what it means. So, okay. So that's a definition from Krasnozelsky about positivity. So here I claim that T2a, my assumption T2a implies that T star is U0 positive in that sense. Since this is the first time you see this, I think, I would like to go through this little proof and prove this property here, so that we can work with the definition a little bit. So I write this down, lemma 1. So T2a implies that T star is U0 positive. So let's do a little proof. So for U0 positivity, we need to show it is U0 bounded from above and U0 bounded from below. We can work with an iterate L to the n, and we need to find an alpha so that U0 is a lower bound, say, for that. So let's look at T star to the n applied to a test function phi. So there would be basically, so we are looking at this here. So then this is by definition integral of T v prime w1 dot 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 T wn minus 1 and v phi of v prime dw1 to dwn minus 1 dv prime. Okay, so T star to the n is the n times iterated operator, so I need the kernel n times integrated with all these w's, and then but then also apply this to phi of v prime. Okay, so then this is integral t to the n of v prime v phi of v prime dv prime. That was a definition of t to the n for the kernel, which I've used in my definition up there, up here, this one. And now I use condition T2a, so that the kernel, where is this, the v prime v, so this guy, so this one is larger or equal u0 of v. So then this whole thing is integral v u0 of v phi of v prime dv prime. Yeah. And now the good thing arises that this u0 depends on v and phi depends on v prime. And I have only one integration. So u0 can be taken out of this. So this is u0 of v and then integral phi of v prime dv prime, like this. Okay, and so now this is my constant alpha, and so then I have t to the n, t star to the n phi is bigger than alpha u0 v. Okay, and this is the condition I need for u0 bounded from below. Okay, and so then bounded from above is then very similar. You will see other inequality here, and then you get a very similar result. So this gives u0 bounded from below. Okay, and then u0 bounded from above is similar. All right. So okay, and then also similar is this condition now. If I use T2b then I have flipped v and v prime from here to there. And so now this relates to the original operator t, not to the adjoint, and then I have the same proof for that case. So now let me tell you why I make all this effort with the t to the n. So I can do that here. Okay. So let's assume I have an incoming velocity v prime which goes straight up. Okay, and now I'm looking at all the outgoing velocities the particle can have. There can be situations where the particles can only turn so much. So let's say there's an angle and the particles can choose all directions in this direction, in this wedge here, but they cannot turn too much. They can only turn a little bit. Okay. Now this operator, so I can define this as an operator t v v prime. This would not satisfy the Krasnodębski condition. This operator would not satisfy my condition, so I cannot use it. But if I use the iterate, then I can. So the iteration means I have v prime, and then if I look at t2, then I can turn twice. So t2 gives me this area, but then I can turn again, so maybe I get this area. So this would be t2, t to the 1. So maybe I need to reorient 3 times, and then I can fill everything. Okay. So maybe t3 goes up to here. So then t4 would cover everything. So in this example, t4 v prime would be strictly positive. So you would be after 4 turns, you would be able to reach any direction. Whereas in 1 turn, you might not be able to reach any direction. And that's the reason I do this. So here in this case, t4 would be the guy satisfying all this, and then I'm in business. Okay, where t itself would not satisfy all this. Okay. So, yeah, all right. Da-da-dum, da-da-dum, like this. So now comes the main result from Krasnodębski, theorem 3. Uh, 1964, theorem 2.10 and 2.11 from the English translation. So. And basically, this is the Perron-Frobenius result for integral operators. So what is Perron-Frobenius? So question to you guys. So what does the Perron-Frobenius theorem say? Maybe first, what is it about? So do you teach that in graduate classes? Perron-Frobenius on linear algebra? Maybe it has a different name. Maybe that's a Korean mathematician or something. So it's about positive irreducible matrices. So you have a positive matrix which is irreducible, and you are interested in the eigenvalues. So you have a leading eigenvalue, okay, and the leading eigenvalue is multiplicity is 1, and the spectral radius is equal to this eigenvalue, and you have a positive eigenfunction, right? So who has heard about this before? A little bit, and maybe in different context. Okay. So so then I write this down. So similar. Let's see. Actually, I write this down in even more detail because it's important. This can go. So Perron-Frobenius theorem. So you have a matrix are in our n times n, which is non-negative and irreducible. So irreducibility means you cannot write or transform this matrix into block diagonal matrix, which are then separate from each other. So you can, yeah, so that's irreducible. And so then the spectral radius of A is a leading eigenvalue with a positive eigenfunction. Okay, and all other eigenvalues satisfy lambda is less than rho of A. So you have a unique leading eigenvector. And here positive eigenvector means it has all positive entries. So there's no zeros anywhere. Positive entries. And it's unique and multiplicity is 1 and all that. So very strong result. And we can do the same thing for the integral operators, t and t star. And this is what Krasnodębski did. So let k be reproducing. Non-negative cone in X. Let L be U0 positive, like I've defined before, and let phi 0 be an eigenfunction in the cone, be an eigenfunction of L. So then, yeah, then we have three properties which talk about the eigenvalue and the multiplicity and all that stuff. So L phi 0 is lambda 0 phi 0, so it's an eigenfunction, and lambda 0 is a simple leading eigenvalue, so the biggest one. Okay, and then second, phi 0 is unique. In K up to scalar multiplication. Okay, and then third, lambda 0 is bigger than all the other lambdas in absolute value for all other eigenvalues. Lambda. Alright, so let's kind of move it up here. Yeah, so there's lots going on. If you have not seen it before, it's quite a bit. But you might be able to appreciate the value of it. We saw in Dr. Matano's talk again that it's always important to know the eigenvalues of an operator, in particular the leading eigenvalue. This tells you something. And here as well. So L will be our turning operators, and I would like to know this lambda 0, the leading eigenvalue. I also would like to know phi 0, the eigenfunction which belongs to it. And then I would like to know that all the others are bounded away from this. Okay. So let's make an observation for our case here. Let's look again at condition T1. Okay. So T1, if I take my adjoint operator T star and apply it to the constant function 1, just see what happens. I take T star which came out here, so t star is this guy, and apply it to the function phi is equal to 1. So then this is integral t of v prime v 1 d v prime. So then I can ignore this 1, it's just a factor. So this is the integral of t over the first variable, and according to the condition t1, that integral is 1. Right? So then this is 1. Okay. But 1, so now comes the major mathematical conclusion of today. 1 is 1 times 1. But they have different meanings. So now the first one is the eigenvalue, and the second one is the eigenfunction. Right? So this is now of the form lambda 0 times phi 0. And here is phi 0. So t star phi 0 is lambda 0 phi 0. So we have them. So phi 0 is a positive function. It is also an eigenfunction. So by Krasnodębski, it must be the unique thing. It is the thing, okay? So this phi 0 here in this complicated theorem is actually just a function 1. Phi 0 is 1. And the lambda 0, the eigenvalue, is 1. So in our application, it is actually super simple. But we still want to make sure that this is the right function we are looking for. Okay? So that makes it for t star. Put it up. And then if I look at condition T4, okay, so in T4, where is the T4? I integrate on the other variable here, so then I get the conclusion for the original operator T. Okay, so then from T4 I get T times 1 is, 1 times 1. So I also have phi 0 is 1 and lambda 0 is 1. So then I have the same eigenvalues, same eigenfunctions for t and for t star. Okay. So that's pretty cool. All right. So let's comment on this a bit more. So T4 looks as natural as T1. But it has a very different meaning. It has a very different meaning. So T4 means that the eigenvalue equation is integral v t of v prime phi of v prime dv prime equals lambda phi of v. Right, so this is the eigenvalue equation for t, for the operator t. And this has a constant solution. Phi of v is equal to 1. Okay. But now this is a very special case. This is very, very restrictive. So what does it mean in our biology? So these are the incoming cells. They have velocity v prime, and then they are redistributed by v. And it basically means the redistribution. If a uniform distribution here, then the outcome is also uniformly distributed. Okay, so yeah, let's see. So which is a very special case. we will see later why it is so special again and again. So I give you later an example where this happens or this does not happen, and you will see that they arise in very different contexts. So maybe just to summarize this a bit. So the condition T1, I said, is very natural because it's conservation of particles. Condition T4 is very different. It is not very natural, and it's kind of enforcing a symmetry on the turning kernel, which we might want to have or might not want to have. So they have a very different function, these two things. Okay. So let's see where I am. Maybe just give you a little preview about the next lecture, but then I do a theorem which needs a little proof, and I will not be able to finish that today. So then I do it next time. So let me just tell you what the plan is. So that would be 3.2. So we use this for the turning operators. So I define LP. So now this will be the full right-hand side of my equation. Minus mu PV plus mu T of PV. And the adjoint L star PV is minus mu PV plus mu T star of P. And so what I've done now, I've talked about the spectral properties of T, and now I would like to use it for L. And L was the right-hand side of my equation. Okay, so then having an eigenvalue 1 here will then correspond to an eigenvalue 0 for the whole thing. So then the leading eigenvalue will be 0 for that thing. Okay, so here I stop, and we can have a little break, and then I continue tomorrow. Yeah, thank you.